Hi, my name is Lexi MacMillan, and this is my SURF poster for 2021. And my research is titled The Investigation of Renewable Surfactants for Herbicides. I worked under Dr. Carpenter in the chemistry department for this research project. So to get started with an introductory slide, this research is based on herbicides. And an herbicide is what kills weeds. And herbicides are able to kill weeds with the chemical glyphosate. And glyphosate is the main active ingredient, which halts protein synthesis and therefore kills your weeds. The literature lately is suggesting that herbicides may be toxic in a lot of different environments. And so as research is going on investigating that, glyphosate was suspected to be the toxic ingredient. However, glyphosate has been shown to not be carcinogenic or toxic. So now research is moving into the surfactants, wondering if they are causing the toxicity. Surfactants are chemicals that are needed in herbicides to help the dispersal of the liquid to get all across your lawn. And they do that by reducing the surface tension, and we'll get into that on the next slide. So the literature is suggesting that surfactants may be toxic to the environment. And so the goal of this research is to synthesize surfactant molecules from renewable sources, namely carbohydrates and fatty acids. And that way, if they're synthesized from a non-toxic source, they will be not toxic in the environment. So this is a representation of a surfactant molecule. And the top is a polar group, which means it's hydrophilic, the same polarity as water. So that allows a surfactant molecule to dissolve in water. In the bottom part, which could be called a tail, is the opposite polarity of water, meaning it's nonpolar, hydrophobic, which means it would not dissolve in water on its own. But when you put these two opposite polarities together, it creates a molecule that can dissolve in water, but also reduce the surface tension of the liquid. So the tail is what does the reducing of the surface tension, but the polar head group is what allows it to still dissolve in water and stay in solution in the herbicide. So to get started on my research, these first two reaction schemes are for carbohydrate head groups. The first carbohydrate used was D-glucose, and the synthesis was sodium bicarbonate and 2,4-pentane-dione, and this synthesis results in a C-glycoside ketone. The ketone is a group with an oxygen double bonded to a carbon, as you can see at the very end of the resulting molecules. And this process was also done with maltose, a disaccharide, to form a different polar head group, as you can see on the bottom, under the same reaction conditions. And this also forms a molecule referred to as a C-glycoside ketone. These molecules will both be used as separate polar head groups attached to different fatty acid tails to create a variety of surfactant molecules. This reaction scheme is for the fatty acid tail, with the first large molecule you see being triacylglycerol, which is more commonly referred to as a triglyceride. These molecules are actually sourced from vegetable oils that can just be bought at the local grocery store. So we went and purchased several of these vegetable oils, including peanut oil, corn oil, olive oil, and several others, to do these syntheses to create a bunch of different fatty acid chains to attach the carbohydrate groups. The R that you see on some of these molecules, R in chemistry is just a long carbon chain, long organic chain of carbons and hydrogens and maybe some other atoms, but it means that that group can vary. So when you vary the type of vegetable oil used, it will vary the properties slightly of the fatty acid group. And what's happening in this reaction is the lipase, you can see as one of the reagents over the arrow, the lipase is cleaving the triglyceride to result in free fatty acids and then also a glycerol backbone as a byproduct. And the fatty acid chain with the 3R on the product side is what we want, and that is what will be attached to the carbohydrate head group. And I was able to start this only with corn oil, but that is as far as I got before my research period ended. So I had just reacted the lipase and the corn oil with the other reagents and then handed it off to the next student. So to finish off this research, there's still a lot of work to do, specifically with what I did. The carbohydrate molecules and the fatty acid molecules will need to be combined to create the surfactant and then test their properties. But unfortunately, due to circumstances out of my control, the GCMS spectrometer is down right now. It was not working. And in chemistry, spectra is really important to identify if we've actually created a molecule. Or you can look at macroscopic properties such as color and texture, but it's really important to have the spectra to know if you've actually made your product or not. So unfortunately, I don't know for sure if those carbohydrate molecules or fatty acid molecules are successful, if the syntheses were successful, or how pure they are. So that will be the task for the next student, is to verify that those were synthesized. And then once those are verified, they will be combined to create the surfactant molecule. And then the properties of interest that they will want to test for may be polarity, penetration, elasticity, shearing, spreading, and drying. And those can be tested in a variety of ways, but those have not been done yet. So that is what the future of this research looks like. So to conclude, herbicides have been suspected to be toxic in certain environments. And so looking at the surfactant molecules, we wanted to attack the problem head on and start to synthesize them from a new renewable source. And so that is what we did using carbohydrates, namely D-glucose and maltose, and fatty acid sources such as corn oil and peanut oil, and create surfactants that way. And surfactants are important because they reduce the surface tension of herbicides. And in the future, hopefully students will be able to expand on this and create an awesome surfactant molecule that could even be used in the future in commercial herbicides if they can perform the same way as current surfactants do. So thank you, Dr. Carpenter, for the help on this research and the rest of the chemistry department. And thank you for watching.